Imagine you're preparing for an important exam. A friend hands you two study books. The first contains only 200 carefully written pages. Every topic is accurate, well-organized, and directly related to the exam. The second contains 2,000 pages. Some chapters are outdated. Others repeat the same ideas. A few even contain incorrect information. Which book would you choose? Most people would choose the first one without hesitation, because we naturally understand something important. When it comes to learning, quality matters more than quantity. Interestingly, many people forget this principle when building AI systems. When discussing machine learning, we often focus on questions like, which model should I use? Should I use the latest architecture? How can I improve my model's accuracy? These are all important questions, but they all assume one thing: the model has something worth learning from. Every machine learning model learns by discovering patterns in data. If the dataset is incomplete, inaccurate, or unrepresentative of the real world, even the most sophisticated model has limited opportunity to learn the right patterns. In other words, before asking how good the model is, we should first ask, how good is the dataset? Many people assume that a good dataset is simply a large dataset. That assumption is often wrong. Imagine you're building an AI system to detect defective products on a manufacturing line. Now compare these two datasets. Dataset A contains 1 million high-quality images collected from the internet, but most of them have nothing to do with manufactured products. Dataset B contains only 10,000 images collected directly from the production line where the model will eventually be deployed. Although dataset B is much smaller, it is clearly the better dataset, because it represents the problem the model is actually expected to solve. This leads us to a simple definition. A good dataset faithfully represents the real-world problem your AI model is expected to solve. But there's an even more intuitive way to think about a dataset. And once you see it that way, evaluating dataset quality becomes much easier. Instead of thinking of a dataset as rows in a spreadsheet or thousands of images, think of it as a miniature version of the real world. Every sample is one observation from that world. Together, those observations teach the model what that world looks like. If this miniature world is incomplete, the model learns an incomplete understanding of reality. If it contains mistakes, the model learns mistaken relationships. If it no longer reflects today's world, the model learns a world that no longer exists. Here's the important part. A model never learns directly from the real world. It learns from the world you build for it. Once you see a dataset this way, evaluating its quality becomes much more intuitive. Instead of asking whether the dataset is large enough, we can ask a much better question. How faithfully does this miniature world represent reality? To answer that question, I like to use a simple framework built around 6 questions. Together, these questions help us evaluate whether our miniature world is complete, trustworthy, and up to date. Let's take a look. Does every sample belong? Is anything important missing? Can I trust the samples? Can I trust the labels? Was the dataset created consistently? And finally, does it still represent today's world? Together, these 6 questions cover 3 fundamental areas: representation, reliability, and freshness. Instead of focusing on model architectures or dataset size, these questions help us evaluate something even more important: whether the dataset itself provides an accurate and trustworthy representation of reality. Now let's begin with the first area: representation. Let's start with the first question. Does every sample belong? Imagine you're building an AI system that can identify recyclable items. Its job is to recognize plastic bottles, aluminum cans, glass bottles, and cardboard. Most of your dataset contains pictures of those recyclable items, but mixed into the dataset are pictures of cats, cars, trees, and people. Those images don't help the model solve its task. Collecting more data doesn't automatically make a dataset better. Collecting the right data does. This idea is called relevance. If removing a sample wouldn't affect what the model needs to learn, that sample probably doesn't belong in the dataset. Now let's move to the second question. Is anything important missing? Imagine you've collected 20,000 images of recyclable items. At first glance, the dataset looks impressive. But almost every photo was taken indoors, under bright lighting, with clean items viewed from the front. Where are the outdoor photos? What about nighttime images, crushed cans, or dirty plastic bottles? If those situations are missing from the dataset, they're also missing from your model's miniature world. This idea is called coverage. Coverage means making sure your miniature world is complete enough to represent reality. A dataset with good coverage doesn't just contain more images, it contains the missing pieces of the real world. Together, relevance and coverage help answer one simple question: does your dataset truly represent the world your model will face? So far, we've focused on whether the dataset represents the right problem, but representation alone isn't enough. Even if your miniature world contains the right situations, can you trust what's inside it? Let's start with the samples themselves. Imagine your recycling dataset contains blurry photos, damaged images, or partially corrupted files. Instead of learning useful patterns, the model may learn from those errors. That's why data quality matters. Now let's look at the labels. Suppose a plastic bottle is labeled as glass, or an aluminum can is labeled as plastic. The images are correct, the labels are not. As a result, the model receives contradictory information during training. Finally, let's talk about consistency. Imagine 3 people labeling the same plastic bottle. One writes plastic, another writes plastic bottle, a third writes PET bottle. They're describing the same object, but they're using different standards. Consistency doesn't mean every image should look the same. It means every sample should follow the same rules. When your samples are reliable, your labels are accurate, and your data is collected consistently, your miniature world becomes much more trustworthy. So far, we've asked 5 important questions. But even if the answer to all of them is yes, one question still remains. Does the dataset still represent today's world? The world changes. Products evolve. Customer behavior shifts. New technologies emerge. As the real world changes, a dataset that was once representative can gradually become outdated. This idea is known as freshness. Consider a spam email detection system. Several years ago, spam emails often contained poor grammar, suspicious links, and obvious promotional language. Today, many spam emails are generated using advanced language models and closely resemble legitimate business emails. The older dataset isn't necessarily wrong. It simply no longer represents the emails the model is expected to classify today. The same challenge appears in many other applications. Traffic patterns change, manufacturing processes evolve, medical knowledge advances. A good dataset doesn't remain good forever. It should evolve as the world evolves. Let's return to those 2 study books. One was carefully written, accurate, and directly related to the exam. The other was much larger, but filled with outdated and unnecessary information. Most people would choose the first one, because we understand that the quality of what we learn from matters more than the quantity. The same principle applies to machine learning. Before comparing model architectures, tuning hyperparameters, or collecting more data, ask yourself one simple question: is my dataset worth learning from? Remember, a dataset isn't just a collection of images or rows in a spreadsheet. It's a miniature version of the real world. Your model never learns directly from reality. It learns from the world you build for it. The closer that miniature world is to reality, the better your model can understand reality itself. So the next time you build an AI model, don't just ask whether your model is good. Ask whether the world you've built for it is worth learning from. Thanks for watching, and I'll see you in the next video.